Printed circuit boards, or PCBs, are everywhere. Most of the time, they are built in several layers, alternating between copper and non-conductive substrate. Copper line holes called vias are used to connect together traces on different layers. As circuits and their components get smaller and smaller, PCB designs are becoming increasingly complex and multi-layered. The traditional keyboard and mouse way for designing and reviewing PCBs is now a limiting factor in their design. Although CAD software like Altium and KiCad have made moves to adjust to these increasing demands with 3D renderings of PCBs, it has proven to still be ineffective, given the 2D interfaces. And reviews are incredibly important, considering the long lead times to create these boards, up to 14 days, and high costs for complicated boards. To sum up our problem statement, multi-layered PCB designs are unintuitive when modeled in 2D. The solution? View and review PCB designs in 3D space using VR.
Are you tired of designing PCBs with your two-dimensional monitor? Exhausted from the overhead involved in simply traversing layers? Introducing NewBoard, a new way to look at printed circuit boards. NewBoard is a PCB review tool that creates an interactive three-dimensional environment, allowing for better intuition about the board and faster review times.
To use NewBoard, open up your favorite PCB design application, KiCad. Here, we are opening a project file that someone on our team has created. We're presented with the front layer of the board first, but we can also toggle the visibility of the back layer using the layer management interface. This is a pretty simple PCB design, but let's use NewBoard to check it out in virtual reality, or VR for short. In our current build of KiCad, there's a new button denoted by a robot wearing a VR headset. Clicking this button opens up our VR application that allows us to view our current board in VR. Hello, welcome to NewBoard. Right now, I'm really just standing in front of a green screen. For now, let's move my physical body to this corner. I have a headset on that can be seen here, and my hands can be represented by the controllers here. As my head moves, so does the floating headset. I can also walk around the room and be tracked in real time as well. To navigate around the VR environment, I can point to a location while holding the trigger on my left controller. When I release this button, I'll be moved to the location of the blue capsule. I can change the direction I face after I teleport by using the left touchpad. Hovering above the left controller is our menu interface. With the use of our left touchpad, we can rotate our menu. Although many of the features on the menu have not yet been implemented, their icons will be familiar to anyone who has used KiCad. Now let's get the board that we loaded up from before. Notice how there are two layers to this board, the front layer and the back layer. Each layer is connected by vias. To pan the board, we group each of our controllers tightly on the sides. This engages our ability to move the board like this, both left to right and up and down. Using the same controls and only changing the motion of our hands, we are able to rotate the board. One thing to notice is how the board will rotate from the midpoint of the controllers. This is intended to give the user the feel that they are actually holding the board in their hand. To enlarge the board, we can continue holding down our controllers and pull our arms apart. With a few motions, we can make the board really big, which is especially useful for fine details on a complicated board design. With the press of a button, I can toggle the grid view. A semi-transparent overlay appears in line with the board, matching the grid in the 2D editor. This makes it easy to see the alignment of different parts of the board. Another key feature in any PCB design tool is to highlight a specific net or signal. Let's say we wanted to highlight this net. We first take off our headset, go to KiCad, and highlight a net on the KiCad interface. Now let's place our headset back on, and we will see the highlighted net in our VR space. Being able to highlight a net in real time is extremely useful for debugging and reviews. Highlighting our nets in VR gives us a completely new view on our PC board design. Let's close this and launch a more complicated design. This is a microcontroller entirely designed with KiCad. This board has many layers, making it perfect for us to show you our Z scaling feature in NewBoard. Let's change our zoom scaling mode to Z scale by clicking this button. This allows us to use our controllers to pull apart the layers. Here is what a highlighted net for this complicated design would look like. To talk about how we made this all possible, let me pass it to NewBoard's team lead, Anton.
Throughout our classes and co-ops at Northeastern, we've come across a wide variety of open source software projects. We've ultimately decided to keep open source at the core of our project as a way to give back to the developer community. A great example of this is KiCad, an open source PCB design suite. We chose to build our tool directly into the KiCad source code. We've also chosen to build our VR environment using Godot, an open source game engine. Although our tool is meant to be used by professionals, using a game engine allowed us to iterate over designs at a rapid pace rather than spending weeks debugging low-level graphics code. This proved extremely useful when developing our user interface. We wanted the control scheme for our tool to be intuitive and easy for anyone to use right after picking it up for the first time. At a high level, our design consists of new modules integrated into KiCad, responsible for generating three-dimensional circuit board geometry, responding to edit interactions, and communicating with the VR front-end. We developed a modular inter-process communication schema. Our front-end is written in Godot and is responsible for translating events from KiCad into visual feedback in the user's VR headset, as well as accepting input from the handheld controllers and sending that to KiCad to process. I'll hand it back to Justin to talk about how we implemented these in the Godot engine.
Hi, I'm Justin. I did a lot of Godot development for this project. For those of you that are wondering what Godot is an open source 3D rendering engine used to create incredible scenes like this one. When designing our rendering engine pipeline, we wanted to split it up into three main components: the board controller, the VR controller handling, and the network module. Let's first start off with the board controller. The board controller handles the rendering of the board. Unfortunately, loading the board layers were not trivial. Luckily, a member of the open source community had implemented this feature in a beta version of Godot. After connecting with him, we were able to use his work and even help him fix a few minor issues with his implementation. The next module we can move on to is the VR controller handling. This module connects to the board controller and handles all of the physical VR controller input commands and sends it to either the board controller or the other UI elements in the system. Lastly, we have the network module. This is used to get our board information and send information back to KiCad if needed. This is a key feature that allows the rendering engine to be controlled outside of its process. The network node in our rendering engine uses our inter-process communication API to talk to KiCad. For more on the IPC, let's bring it over to Mark.
Thank you, Justin. Since the majority of the board design is done with KiCad, we needed a way to transfer that board to Godot for rendering in VR. This is done with a custom communication protocol. The left side of the screen represents the KiCad server. The right side of the screen represents the Godot client. The process begins with the user starting the VR session from KiCad. Once the client has fired up, it connects to the WebSocket via TCP, and it sends the setup message. KiCad immediately responds with a position message, describing the XY offsets of the board geometry files, and a load layer GLTF message, describing where to find the board geometry files. Upon the menu selection in VR, we send an action command, and thus triggering a new load layer GLTF message to be sent. If a user makes an edit in KiCad, it will once again trigger a load layer GLTF message to be sent. Eventually, the communication between KiCad and Godot come to an end. The server and client are agnostic to each other. One half could be mocked to test both halves independently. Let's bring this conversation over to Anton, who can talk about the 3D GLTF geometry writing process in more detail.
The process of connecting KiCad to a real-time virtual reality environment is quite an engineering effort in itself, but it's only useful if we can actually view designs in VR. For that, we need KiCad to generate a data format that our Godot frontend can recognize and render as a three-dimensional object in the VR headset. KiCad has an existing 3D renderer, but it only renders a static image on a 2D window. In that rendering mode, KiCad iterates over high-level board features like traces, vias, and component footprints, collecting them into lists of triangles in memory. Along with a few architectural changes, we were able to use the same rendering logic as a model for the implementation of our own GLTF exporter. Let's have Ashwin talk about how we actually launched the Godot VR view from KiCad.
Thank you, Anton. Hi, I'm Ashwin, and my work consisted of integrating our project with KiCad. As the goal is to extend the KiCad experience, we must be able to launch the Godot engine for VR viewing from within the application. To accomplish this, we created a launch button in the PCB editor tool within KiCad. KiCad registers changes to a board in the form of what are called board commits. By leveraging the board commits mechanism and incorporating our own logic into the application, KiCad is able to process and send any board updates to Godot in real time, and then instantaneously see their changes reflected in Godot. Now I'll send it over to Mike to describe how we send Anton's geometry over to Godot now that we've got it open.
Thanks, Ashwin. While the mock server which Mark discussed was great for rapidly prototyping Godot, we had to implement the real server functionality in KiCad. This meant using libraries which KiCad was already connected to, like Boost and WX widgets, to turn KiCad into a WebSocket server. Similar to how Godot was mostly developed using a mock server, KiCad was developed using a mock client. This allowed both to be developed in parallel so that they could be connected at the end. The WebSocket server, which was a singleton in the KiCad process, was made using Boost 1.72 WebSockets. The Boost libraries also provided many tools for asynchronous communication, which were heavily utilized to create a robust web server. The server can handle an arbitrary number of clients, meaning that theoretically, several Godot instances could view the same board simultaneously. After we got the server running reliably, it was a relatively simple task to write the generated GLTF files to disk and send a message to all connected Godot clients telling them where they can find them. Finally, I'm going to hand it over to Inga to talk a little bit about UI and some closing thoughts.
Hi, I'm Inga, and I did a lot of the UI research and design for this project, and I also designed the menu. Unfortunately, we were unable to fully implement the menu due to the unexpected COVID outbreak. However, I would still like to show you what this project could possibly do in the future. Eventually, we would like to be able to make edits to our PCB directly from the VR environment, and that's mainly what the menu would be used for. If you actually take a closer look at the menu, you can see that all the icons are buttons that you see in KiCad, and they would have the same functionality. The idea is you would select a button on the menu with your right controller pointer. Your controllers would change functionality based on which button you selected. This menu is the edit menu. It contains all the tools that manipulate the functionality of the PCB and PCB documents. This menu is your visual menu. It changes the way you see things within your VR environment. Another very promising direction this project is going in is collaborative editing. What I mean by this is multiple engineers in the same VR environment working on the same board. Now more than ever, we're seeing the need for collaborative, hands-on yet remote design. Last but not least, this project would not have been possible without the wonderful contributions of the open source community around us. Specifically, we would like to thank K.S. Ernest Lee, who wrote a special branch of Godot that could render GLTF files at runtime, without which our project would literally not be possible. We would also like to thank Seth Hilbrand and the rest of the KiCad developers. And of course, Waleed. Thank you for a wonderful semester despite global catastrophe.